To move data across any modern network, abstract digital information must be transformed into physical electromagnetic signals. This transformation is restricted by the degradation of the physical transmission medium, environmental noise, and strict mathematical capacity limits. These physical layer constraints define the functional limits of every real-world network. This side-by-side comparison illustrates the two formats data can take. On the left, analog signals are continuous and take on an infinite number of values. On the right, digital signals are discrete, limited to a specific number of defined states. In practice, data transmission rarely relies on a single wave. It requires composite signals constructed from multiple interacting sine waves. When sending digital signals directly over a channel, networks use baseband transmission, which operates starting at a frequency of 0. Alternatively, broadband transmission is used when the medium requires that digital data be converted into an analog signal to survive the journey. The physical properties of the transmission channel dictate which of these formatting methods must be used. Regardless of the format, physical transmission media inherently degrade signal quality as it travels over distance. This diagram shows the first major impairment, attenuation. As the original signal moves from point 1 to point 2, it loses energy and flattens out. Network architects solve this by deploying amplifiers along the route to regenerate the signal's power before it reaches point 3. The second impairment is distortion, which occurs when a signal shape is altered because different frequencies arrive out of phase. Finally, signals face noise, interference from heat, crosstalk, or outside impulses. The metric of a channel's health against this interference is its signal-to-noise ratio, or SNR. Managing these three specific impairments is necessary to maintain a viable SNR. A channel's bandwidth represents a rigid mathematical boundary, governed by two foundational laws. The Nyquist theorem calculates the absolute maximum bitrate possible in a theoretical, perfectly noiseless channel. Shannon's capacity defines the true limits for real-world noisy channels, factoring in the signal-to-noise ratio as a primary variable. To increase data rates in the real world, you must either expand the physical bandwidth or improve the SNR. Bandwidth describes a link's theoretical potential, while throughput measures the actual amount of data successfully delivered. The gap between potential and delivery is caused by latency, which is composed of 4 physical components: propagation, transmission, queuing, and processing delays. Troubleshooting a slow network requires isolating which of these 4 components is the actual bottleneck. At the physical layer, engineering is bound by the laws of physics. Optimization relies on balancing mathematical trade-offs between signal power, noise reduction, and latency management.